In the last video, we learned about the projectile motion equations. We defined them all, listed and summarized them, and now we're going to put them into practice a little bit. So first of all, I'm going to take a ball, and I'm going to throw it up into the air. And I want to know, how does the time to the top of the flight correspond with the time down? And how does the speed of launch compare with the speed coming back down? Now, before you answer too quickly, remember that on the way up, gravity is, let's see, is it helping or hindering? That's right, it's hindering. So on the way up, it's hindering its motion. On the way down, gravity is helping its motion. So I'm sure you've concluded that the time down is less than the time up, right? It would take longer to go up because gravity is hindering it. And then, how about the speed? Launch versus come back to hand, whack, and up here it's 0. Well, maybe I should backtrack in my assumptions about what you're thinking. I don't know what you're thinking, but regardless of what it is, let's clarify those thoughts. So the vertical equation is equation 3 that I want to use. Vy is Vy0 minus gt. It's a good equation for vertical motion, especially if we're talking about, well, we've got time and we've got speed, so it relates. Well, what is Vy at the end? The end, namely, is at the top. Well, by definition, if it's at the top, it's come to rest, 0. So let's solve it. So we know that at the time that we're looking for, the time we're looking for is when this is 0. So that's what we're going to solve. Vy0 equals gt. T, I'd use the subscript up arrow, T up, equals Vy0 over g, and it's very simple to plug and chug now. 25 over 10, T up is 2.5 seconds. Now we know the time to the top. Let's go ahead and solve. I didn't ask for this initially. I'm asking for time and speed up, time and speed down. But I'm going to go ahead and deviate a bit here and solve for the maximum height. Let's do that. So here's our equation 5 that gives everything about position. Position is really good. It's got acceleration and time in there. We have all that now because we're looking for the position at 2.5 seconds, which I'm hoping you realize will be the maximum height because it's at the top of its flight at 2.5 seconds. So let's solve this for, see, what are we going to solve it for? We're going to solve it for this y. We're looking for y after 2.5 seconds, which is y max. So then it's, considering y0 is 0, Vy0 time up minus 1/2 g time up squared. So that's how I wrote this. That's 25 times 2.5 minus 1/2 g is 5 times 2.5 squared. Numbers, result. Y max, 31.25 meters. So that's the top of its flight. That's actually really pretty high up, but that's beside the point. Another way we could have gotten the height. Could we get the height if we didn't know the time to the top of the flight? Well, the answer is yes, and it's using equation 6. So I'm looking for this, the height of the ball. Recognizing that at the top of the flight, Vy is 0, so this part is 0. That'll be helpful. Solve for h. Do we have everything we need? Well, let's see. H is Vy0 squared over 2g. Do we have Vy0? That's initial vertical speed. Yes, that's our 25. And 2g is known, so plug it in. 25 squared over 20. 31.25 meters. So it indeed gives us the same result, and at this point we know the time up to the top of the flight, and we actually know the height. Let's now get the time and speed going back down. Let's now go ahead and analyze the path back down. So we've gone up, and we're gonna go back down. So we have a situation where here's the ball up at the top, and we're going to, in the final position, it's down here. This would also correspond to the final velocity that we're trying to find. We know the height It's 31.25 because we've already solved for that. Vy0 equals 0. That's really important. Before, Vy0 was down here and it was 25 going up. So the equation for the time down, I'm going to use equation 5. The change in vertical position equals Vy0t minus 1/2 gt squared. So we had t in here. We know what this is. We know what this is. We got everything in the bag here. Vy0 is 0. And so the whole thing is 31.25. Actually, minus 31. Why did I put minus? Final minus initial. So the initial is a bigger value and you're subtracting it. Now, solving this, we have delta y and we have 1/2 gt squared. So I'm just doing the algebra to solve for t squared. Minus 2 delta y over g. So t down, the t we're talking about is the time down. And it's square root of 2h over g. I now drop the minus sign because this is negative as well. And the value of this, the magnitude, is the height. So the difference in positions is the height of the ball. Plugging the numbers in, we get, probably not too surprisingly, 2.5 seconds. So indeed, the time to rise up equals the time to fall down. Now, I was trying to trick you in saying that gravity is hindering going up, helping going down. But the difference is, going up, yes, it's hindering, but we're starting with 25 meters per second. Going down, we're starting with 0. And gravity is helping to speed it up. Here we're starting with 25, and gravity is hindering to slow it down to 0. And bottom line is they're essentially symmetric operations. They're doing the same thing. Does that make sense? You know, you're starting with 25, ending at 0. You're starting with 0, ending at 25. All right, so that's true then for all normal situations of time up and time down. Now the speed going down. We had 25 meters per second initially. You probably can guess how this is going to turn out. I'm going to use equation 3. The vertical speed or velocity. And typically, a lot of times, whether you say speed or velocity doesn't matter. Technically, this is an equation for velocity. Well, it's 0, because Vy0 is 0, minus 10t, simplifying g to 10 from 9.8, gives us minus 10 times 2.5, and sure enough, the answer is that the final speed is 25 meters per second, so I filled that in. But we could get the speed in an alternate way. Once again, we can bring out equation 6, which does not include the time, recognizing that the initial velocity is 0, right? And we can solve for Vy. Vy is square root of that other stuff. Notice again, I dropped the negative because this is negative. Equals 2 times 10 times 31.25. Square root of the whole thing is 25 meters per second. Yay! Now, conclusions. Basically, in vertical projectile motion, which is what we're talking about here, it's also free fall. Free fall is a term for gravity only acting on the object. Nothing else but gravity. It's freely falling under the influence of gravity. The time to rise to the top of the path equals the time to fall down. The initial speed up equals the final speed down. Also the total flight time. Time up, down, up, down, up, down. The time up and down together is twice the up time or twice the down time. They're both the same, and if you add one to the other, you get the up-down time. So that's something to keep in mind as well. Now, we've already seen that the horizontal and vertical motions are independent of each other. Therefore, the above conclusions would apply to two-dimensional projectile motion. Here we really have projectile motion, but it's just a single dimension, vertical. So if we add the x component now, if we add the x component, because of the independent nature of these two motions, these conclusions we have are all apply. So the main thing with projectile motion that's not just vertical is that we apply the vertical equations just like before and add the very simple horizontal equations to complete the analysis. Now, if you don't mind, well, and even if you do, I want to show you how to find the total flight time of that previous motion of the ball up and down with a single equation. So we're going to look at the whole path. We have the ball starting here, going up, up, down. That's right. Comes back down. Goes up, comes down. Now, the idea is this is going straight up and down, but I wanted to show you the whole path, so I didn't want to just have a line going up and back down again. All right. Vy is equal to 0 up at the top. And now here's a couple things to know. So the position of the ball at the beginning and the ending of the flight is, what would be a logical position to call this? That's right, 0. So our equation 5 to solve for the time, here it is, the full expression, final position, initial vertical velocity, acceleration, with the time in there a couple of times, gives us the ability to do this all at once, knowing that initial and final are both 0 positions. So we have Vy0t minus 1/2 gt squared, and you see how time divides out, at least on one side. And so we have time up and down equals 2Vy0 over g. Now, I really like boxes, so it's not like you're going to memorize this equation. I would not do that. You've already got this one memorized, and you can solve, in this particular case, for this, given that y and y0 is 0. All right, so now I'm going to give you a little personal disclosure about something I did some years ago, and not as many years ago as I would almost want to care to admit, but I was living in Lake Forest, and I shot an arrow for a brief period of time, taking care of some person that needed care. My wife and I were, and I had my 80-pound compound bow, and there was a time I went out and I thought, you know what, wouldn't it be nice to shoot this straight up in the air and see how high the arrow goes. I'm not going to implicate myself totally on this video, but I am going to just let you know that it wasn't a real smart thing to do.
Hey, I got a good idea.
Yeah, really good idea. I'm going to assume it took 20 seconds to come back down. Turns out it had a close encounter with a car. So maybe I'll describe that more for you in class if you want to know the details. In any case, assuming it took 20 seconds to hit the ground, what was the initial velocity? Well, we just derived the result for the time up and down, which is 20 seconds. And so that should help us, knowing that Vy0 is 1/2 gt. Okay, that's what we have here. Vy0 is 1/2 gt. And that's equal to 1/2 g 10 t 20. That was the total flight time. And that gives us 100 meters per second. So that was Vy0, 100 meters per second. So this equation is very useful, equation 5, especially because it has time in it, and time is a very useful physical quantity when we're solving projectile motion problems. And it's got a lot of other stuff in here as well that we're able to utilize to our advantage. The other very powerful equation is equation 6, if you don't have time. Oh, and we don't have time to progress along this video anymore, so let's bring it to a close, and we'll do some more examples next time.